Assalamu alaikum. Welcome to lecture 18 of data mining. So in the last lecture, we had discussed clustering and started discussing clustering, and we discussed similarity measures and functions. And then after that, we kind of characterized clustering and also did a bit of categorization of clustering algorithms and types of clusters. So today, primarily we'll be discussing the k-means clustering algorithm, which is a partitional clustering algorithm. And so if we have time, we will discuss some variations and extensions to the k-means algorithm, like the k-modes and the k-methods as well. So that's the agenda for today. So today is Tuesday, so we do have a quiz at the end of class today at around 1:35 p.m. All right, so are there any questions? All right. So we are going to discuss the k-means. So the k-means clustering algorithm was proposed in the late 60s and early 70s. So it's a fairly old algorithm. It really became popular in the 1970s. And as I mentioned earlier, for clustering as well. So it is now widely used in different fields, from the sciences to the social sciences to the business community. So it's a very popular algorithm. So the k-means algorithm is a partitional clustering algorithm. So we discussed some categorizations of clustering algorithms last time. So there was partitional, there was hierarchical, and you may have other types of algorithms as well, like model-based and so on. So this is a partitional clustering algo. And it will become clearer why it's called partitional as we move forward. So let me just highlight some of its key characteristics, and then we'll discuss the algorithm in more detail. And secondly, it is prototype based. The clusters that it defines are prototype based or defined by points or objects. So prototype based clusters. So the clusters are defined by some points, usually one point, which is the mean in this case. That's why this is called the k-means. And so this algorithm is also if you want to add this characterization, in general is hard clustering, although it can be extended to soft clustering very easily. But the traditional form is hard clustering, meaning that every point would lie in one cluster only. So it's hard clustering. And what else? It is so it's based on, it's basically, it uses an objective function and it's optimization based, meaning that there is a objective function that is minimized implicitly during the k-means process. So it's not heuristic, it's more, you can say, mathematical. So there will be some techniques that are heuristic in the sense that they do not provide guarantees. The k-means algorithm is not like that. It's based on an objective function that is optimized or it's minimized in some way during the process. Okay? So these are some characteristics of the algorithms. Of course, there will be other characteristics that are related to the types of clusterings that is formed. We will discuss that later on. So it's a partitional algorithm. So it requires the number of clusters as input, which of course is k, the number k. Just a second. So you need to provide k as an input to your algorithm. So the number of clusters that are desired. Okay. So that is kind of characteristics for all partitional algorithms. So you need to tell the algorithm how many clusters you want a priori before even the algorithm starts to run. Then, of course, let me write the data set. Let's say the data set, of course, is a set of points xi. Of course, I is equal to 1 to n. There are n data points that we want to cluster. So x in general is a vector. Okay? Ith object is represented by the vector x, and x vector of size, let's say, m. Okay? So each object is represented by a vector of size m, and also vector of numeric values. So the k-means algorithm, this is kind of a characteristic of the k-means, which is, you can say, both a limitation as well as a, you can say, benefit in the sense that it's fast. It only works on numeric attribute values. So the vector x represent features that are all numeric. Okay. And then for this vector, usually since it's all numeric, usually we're talking about the distance function as the Euclid, although this can be changed, but the traditional k-means is based on the Euclidean distance. So the Euclidean distance is used as the dissimilarity function. Okay? So we have the data set n points. Of course, k is much less than n. We need k clusters. N, of course, is the total number of data objects. And clusters must satisfy an objective function. So what is that objective function? I will write that now. So objective function, cost function slash cost function. So let's say the cost function for the clustering is this. Sum for all objects I. Okay. So we have an indicator function, object I and cluster K. Okay. All right. So let's say indicator function R, let me capital small it. Okay. R I K. Okay. And then this is written in vector notation X, or let me write it in the other form first. Okay. So D X I and M K. So of course these are vectors. So I, of course, is the object representing the object of the n object. So I goes from 1 to n. Okay. So what is mk? Of course, what is k? K is the number of clusters, or is the cluster ID, and of course this goes from 1 to of course k, which is the desired number of clusters. So I'm writing the desired number of clusters as capital K, and this small k is the index. ऊपर शायद मैंने वो भी small लिखा था, but correct that. So the desired number of clusters is capital K, just like the total number of objects is capital N. Okay? And what is RIK? RIK. So this is an indicator function, which basically is so RIK is equal to 1 if and only if object I belong to cluster K. Otherwise, otherwise, ठीक है. So it's a 1-0 function, indicator function. So essentially, अब ये वापस हम इसको देखें, objective functions, what is it doing? So it's a sum over all objects, and only we are counting the sum of the distances of each object from its mean. Okay, m मैंने define नहीं किया. So mk is the mean of cluster K. ठीक है? So what we are doing is we are summing up the distance, which is the Euclidean distance of every object from its mean in the data set. And the indicator function, of course, is only saying that we are summing the distance of every object from its respective cluster mean. ठीक है ना? तो let's say हम उसका distance with other means ना add करें, so वो 0 होगा indicator function, so that sum is not added. ठीक है? So in layman terms, the cost function C is the sum of distances of all objects from their respective cluster means. Okay? So this is what C is. So this is the objective function that we are minimizing. So this is the clustering criterion. And why is this relevant or appropriate for clustering? Because we would like clusters whose this cost is small, meaning that objects lie close to their means, meaning that those objects, and the means, of course, are the representative of each cluster, the prototype for each cluster. So if you have this value as small, then it means that the clustering is good. If the value is large, it means that an object is assigned to a mean that is far away. It means that that object probably is not part of that cluster. Okay? So this is the objective function that we actually minimize or try to minimize in this K-means algorithm. So in essence, it is an optimization problem that we are solving. Unfortunately, this optimization problem is non-convex, and the algorithm that we will use would only guarantee a local minima, not a global minima. Okay? So this is from optimization theory. If you have a convex optimization problem, using a gradient descent approach would lead to a minimum that is also the global minimum. There will be just one global minimum, and you will be able to find that. While in non-convex problems, you might find a minimum, but it might not be the global minimum. It might be a minimum in the set of possible miниmas. All right. So that was the objective function. So now what is the algorithm to kind of minimize that objective function? So let's discuss the algorithm, then we will then say why it works. We'll see why it works. So the algorithm is, so initially you have n data points. So since k is an input, so what is the input? Of course, k, and of course the data set D. Okay? So K is an input. So initially, I'm going to write the algorithm in kind of non-standard format, kind of English. So basically, select K initial means. So this is starting. So you have selected K initial means, and you can typically will do it randomly. Okay. And of course, later on we will discuss some other techniques. And then we do a loop. So for, let's say, whatever, from iterations, these are iterations. So let's say T is equal to 1 to capital T, the number of iterations. Okay. And then that's one loop. Then we have the other loop from I is equal to 1 to n number of objects. Okay. So we have two loops here. And then we assign object I to the mean to which it is the closest. Meaning that, again, remember, we want to minimize the sum of distances to the mean. So we'll assign the object I to the mean. Remember, we have selected the means randomly initially. So now we are assigning each object to the mean that is closest to it. So of course, the mean is representing the cluster. So once you have done this for all the, so end loop I, okay? So when you have done this for all I, you basically now calculate mean again for all clusters. And then, of course, end loop, the other loop was T, iteration. And of course, when do you stop? You have a stopping criteria here, maybe. Uh, uh, so the stopping criteria could be a couple of stopping criteria, meaning that you get out of the iterations loop, and the stopping criteria, let me write it separately because I'm not writing the algorithm in a pure form. So the stopping criteria could be one, when assignment of objects do not change from one iteration to the next. Okay? So remember, we have n objects. So in iteration 30, let's say, those n objects were assigned to their respective means. Okay? In iteration 31, there was no change in assignment, meaning that all those 30 objects were still assigned to the same clusters. If that is the case, then you can stop because there is no change in the clustering. Okay? So that is one stopping criteria that you can use. The other is, of course, based on the cost function. If cost for the iteration t plus 1 minus cost for the iteration t, and of course, some you may want to do an absolute on this. It's less than some small number, epsilon. Okay? Then you can stop. Meaning that, again, this cost would not change when there is no change in assignment. But let's say there is some change in assignment from one iteration to other and you're still not converging completely, you can use a small epsilon to determine when you want to stop. ठीक है।
जी सर।
जी क्वेश्चन।
यस सर। सर टी जो लूप में मेंशन्ड है, ये इससे क्या पता चला टी है क्या एग्जैक्टली?
थोड़ी सी आपकी आवाज़ कम आ रही है, जस्ट गिव मी अ सेकंड, मैं वॉल्यूम बढ़ा दूं। जी आप बोलें।
सर आप आवाज क्लियर है?
जी बेहतर है जी।
सर लूप में टी मेंशन्ड है, तो टी एक्चुअली है क्या?
टी आइट्रेशंस है, मतलब आप कह लें ये वाइल लूप है। ठीक है ना, तो टोटल नंबर
सर
ऑफ।
मतलब
जी
किसकी बेसिस पे ये इटरेशन, पहली वाली इटरेशन रन होगी, लाइक अपर बाउंड क्या है?
अपर बाउंड इसका सच कोई नहीं है। एज अ सेड, ये आप समझ लें कि ये वाइल लूप है। आप चलाते रहेंगे अंटिल योर स्टॉपिंग क्राइटेरिया। ठीक है ना, तो
ठीक है
स्टॉपिंग
सर।
क्राइटेरिया सेटिस्फाई हो जाएगा तो उस लूप से बाहर निकल आएंगे, मतलब आपकी क्लस्टरिंग कंप्लीट होगी। ठीक है, स्टार्ट क्लियर।
यस सर।
ठीक है, तो वो टी मैंने इसलिए वहाँ एग्जैक्ट लिखा है कि बिकॉज वो टी फिर वो कंप्यूटेशनल कॉम्प्लेक्सिटी में वो नंबर मैं यूज करूंगा, तो दैट्स व्हाई आई रोट द एक्चुअल टी देयर, कैपिटल टी, ऑल्दो दैट्स नॉट समथिंग दैट इज नोन ए प्रायरी, that would be the final number of iterations before your algorithm has stopped. ठीक है, ठीक है। सो essentially ये दो stopping criteria हैं। so so essentially इस algorithm में it's again very simple algorithm. You start with some random calculations of the means, k means, and then based on those means you assign objects. Once you have assigned the objects, the means are recalculated because each cluster will be defined by the objects to which it is assigned. ठीक है, and then you take the mean of all those objects to find the new mean. Once the new mean is computed, you repeat the process until there is no change or the stopping criteria is invoked. All right. And of course, we are assigning points to the nearest mean, which is uh, intuitively minimizing your cost function. Of course, this is not intuitive, this is correct, but of course the theory थोड़ी सी deep है, थोड़ी सी मैं introduce करूँगा later on. It's based on expectation maximization, but we won't go into much depth of that. ठीक है. All right, so let me take a very simple example and then we'll come back to the algorithm. Very simple example, 1D data set. ठीक है. So 1D data set मतलब ये है कि simple numbers हैं. So you can take some numbers, let's say, so let's say मेरे पास data set है, let's say 5, 7, 8, 9, 11, 13, 15, 16. ठीक है. तो ये मेरे ख्याल से N8 बन गया शायद. ठीक है. So 5, 7, 8, 9. So these are 4, then 11, 13, 15 and 18. 8 points. ठीक है, 16 है. ठीक है. So let's say you have these 4 points and let's say initially, again let's say randomly मैं लेना चाह रहा हूँ, तो let's say मैं randomly कोई दो means ले लेता हूँ. एक mean let's say कहता हूँ, so actually k of course मैं कह रहा हूँ कि 2 है. Number of clusters that I desire is 2. Of course this is an input. ठीक है. तो random initial means let's say m1 मेरा let's say 10 है, let's say m2 मेरा let's say 12 है. ठीक है. So what do we do? Means आपके पास पहले आ गए, you do assignment. So पहला ऑफ कोर्स ये डिस्टेंस 1D है तो यूक्लिडियन डिस्टेंस मैनहट्टन डिस्टेंस दोनों सेम होंगे, ठीक है ना. सो 1D 5, पहला पॉइंट था 5 6 7 5 7 8 9, ठीक है ना. सो पहला पॉइंट 5 है. So 5 would, let's say, cluster 1 and we have cluster 2, ठीक है. क्लस्टर 1 ऑफ कोर्स M1 का अभी जो मीन था वो 10 था. तो 5 इज इट क्लोजर टू 10 और इज इट क्लोजर टू 12? इज क्लोजर टू 10, सो 5 इधर आ गया. व्हाट अबाउट 7? 7 भी इधर आ गया. 7 इज क्लोजर टू 10 देन टू 12. देन व्हाट अबाउट 8? अगेन इधर आ गया. 9 अगेन इज क्लोजर टू 10 देन टू 12. एंड देन उसके बाद मेरे पास आता है 11 है. 11 is again closer to 10, right? Then to 12. 11 is closer to 10. दोनों बीच में है, ठीक है. So this is a tie. Whenever you have a tie, you can take a random choice. So let me put it into cluster 1. So 11 is equidistant from 10 and 12. ठीक है. तो अब 13 देखें. 13 is it closer to 10 or 12? It's closer to 12. So it goes into cluster 2. So it goes into 2, 13. Similarly 15 भी इधर आ गया और 16 भी इधर आ गया, ठीक है. ऑफ कोर्स ये 1D था. 2D के लिए आपने प्रॉपर डिस्टेंसेस निकालने. यहाँ भी डिस्टेंसेस निकाले हमने, बट ये सिंपल कह लें कि मेंटल मैथ हमने कर ली, ठीक है. सो नाउ वी हैव दीज नंबर्स एंड नाउ वील हैव टू रिकम्प्यूट द मीन. अब इसका नया मीन निकलेगा, ठीक है. ओके, स्टॉपिंग क्राइटेरिया बीच में आ गया. सो लेट्स से अपडेट मीन्स. So how do we do that? We compute the new mean of M1 is equal to how many points do we have here? I think 5, right? So the new mean is 8. ठीक है, we have updated the mean. So similarly for M2 में मेरे पास है 13, 15 and 16. 13 plus 15 plus 16 divided by 3. So the new mean is 14.67. ठीक है. So 8 and 14.67. Of course, if these were vectors, तो vectors mean निकालने थे. हर एक element का mean निकलना था, ठीक है. So here, of course, they are 1D. So 1D, of course, is one element, one value. So now you assign again. So assignment. So 5 is closer to 8 or 14. It's closer to 8. So 5 goes here. 7, is it closer to 8? Goes here. What about 8? Again to 7. What about 9? Again to 8. And what about 11? 11 is 11 का distance है 8 से 3, right? 11 minus 8 is 3 and 14 minus 11 is 3.67. तो यहाँ भी 11 भी इधर ही रहा. Actually there is no change, but let's see. The next था 13. 13 of course is closer to 14. ठीक है. So closer to 14 to 13 इधर नहीं आएगा इसको. So cluster 2 is of course remains the same, 13, 15 and 16. So you notice that there is no change in assignment. After one iteration, we have found the clustering. Of course, this is a simple problem. I just did it from memory. Sometimes for such simple problem, maybe it requires one more iteration, but usually it will converge. Okay, and of course, means also would not change. Since assignment has not changed, mean would also not change. So the final clustering is this last clustering in which objects 5, 7, 8, 9, and 11 belong to cluster 1, and objects 13, 15, and 16 belong to cluster 2. ठीक है, is this clear?
सर अगर मीन चेंज नहीं होता तो ये स्टॉपिंग कंडीशन है इसकी,
जी
वरना वी विल
जी जी
हम रिकैलकुलेट करते रहेंगे जब तक मीन सेम नहीं आ जाता.
जी मीन ना चेंज होने पे भी आप एक स्टॉपिंग क्राइटेरिया बना सकते हैं. जी ठीक है, मीन ना चेंज होने की या कॉस्ट फंक्शन ना चेंज होने की या असाइनमेंट ना चेंज होने की, ऑल ऑफ दिस कैन बी यूज्ड एज अ स्टॉपिंग क्राइटेरिया. Because cost function, by the way, क्या होगा? Cost function, if I write the cost function for this, it would simply be, let's say पहले का mean 8 था, तो cost function for this final clustering is what? Is basically 5, of course, let me write in that sense, D 5, 8 plus D 7, 8 plus D 8 भी था, 8, 8 plus D क्या था 9 भी था, 9, 8 plus D 11, 8 plus D था मेरे पास 13, 14.67, दूसरा क्लस्टर आ गया, plus D. This is where the indicator function works. So ये अब उसके साथ निकाल रहे हैं, पहले के साथ नहीं निकाल रहे हैं हम. ठीक है, दूसरे असाइनमेंट दूसरे के साथ है. So this is 15, 14.67 plus D 16, 14.67. So this is the final cost. ठीक है. So this was 1D. In general, if it is m dimensional, MD, as we said, mostly we will use Euclidean distance. So Euclidean distance, so sometimes what we do is the cost function is defined as, जैसे पहले कहा था sum I R I K, right? Then we have simply a vector notation में अब लिख रहा हूँ मैं, xi minus m k. Vector is a column, so I take the transpose and then xi minus mk. So Euclidean distance is actually the square root of this, and this measure is actually the sum of squared errors, or the square of the Euclidean distance. Okay, so this is also sometimes used, and both of them are equivalent from an optimization perspective, because monotonic square root और square से कोई फर्क नहीं पड़ेगा minimum पे. ठीक है, so this function of course is called the sum of squared error, or oftentimes you will see this name being used in k-means, the sum of squared errors as the cost function. So what is the error? The distance of, or the inner product of the difference between the vector and the mean. Okay. उसका स्क्वायर हुआ, 2 दफा आ रहा है ना, तो स्क्वायर किया उसको, sum of squared error. So this, if you are using the Euclidean distance, so this is also equivalent to, of course, sum I r I k d x I m k whole square. तो यूक्लिडियन में स्क्वायर रूट होता था, तो वो स्क्वायर रूट को आपने उड़ा दिया, ठीक है. So error is the distance, और फिर square कर दिया, तो which is, that's why this is called sum of squared error. All right. So this is the k-means algorithm. So as you can see, the algorithm itself is pretty easy. It has just one or two steps actually. One step is the assignment step, where given the means, we do the assignment. Okay? So, and the other step, of course, is given an assignment, we find out a new representative for each cluster, which is the new mean. So there are two steps. So two-step process. And in the statistics and machine learning community, this is actually a generic two-step process, which is often known as the expectation maximization algorithm. So what are the two steps? One is the expectation, one is the maximization. Maximization, of course, here is the minimization. And what is the minimization step? The M step. The M step is the assignment. You are minimizing the cost. And what is the E step? Calculating the mean. Okay? So actually the k-means algorithm is the expectation maximization algorithm for solving this optimization problem of minimizing the sum of squared errors of every point from their respective clusters. So EM is actually a technique for solving optimization problems. And of course, if you want to understand EM more detail, you have to introduce probabilities. We won't go into that in this course. Okay? So, but I hope you understand the M step is actually the assignment step. Why is it M step? Because it is minimizing the cost, the error. Okay? And maximizing, this is where you, for a given state of means, and of course the mean step is once you have the assignment, finding the next representative, the expected value. Expectation, of course, is the mean. Okay? Calculating the mean. And you repeat this until there is no change or your stopping criteria is invoked and you stop. Okay. So now a few other things. I think I lost my thought process. Okay. So there are a number of things to be discussed. I'm just thinking which we wanted to start next. Okay, the computational complexity. So what is the computational complexity of this? If you notice previously in the algorithm, you have t iterations, and within each of those t iterations, you iterate over n objects, right? And then within those for each of those n objects, you assign the object to the nearest cluster. How many clusters do we have? K clusters. So you have to do k comparisons for each object over t iterations, so which basically gives you O n k t as the complexity, time complexity. Okay? N objects, k clusters, and t iterations. So this is actually quite efficient. And actually, this is the strongest uh, positive for the k-means algorithm. There's no other clustering algorithm which is as efficient as the k-means algorithm. Okay? It's linear in all its parameters, the number of objects, the number of clusters, and of course, iterations t. In general, as I said, k is generally much less than n, and also t in general would be much less than n. So these numbers are generally small. Okay? So it is an efficient algorithm. So that's a big positive for the clustering algorithm, and that's one of the reasons for its popularity as well. All right, so now let's talk about some characteristics of the k-means clusterings, uh, and which would lead to some positives and some negatives, and then we'll discuss some ways of avoiding those negatives. Okay? So some of the characteristics we have already mentioned before is optimization based, it is partitional, it requires k as an input. So some of these may be considered positives, some of these may be considered negatives. So you can add them here as well. Uh, so in addition to that, so let me just write them and maybe repeat them. So what are the positives, benefits, or you can say positives? So positives, of course, is optimization based, not heuristic. It has a criterion. Uh, criterion is explicit. It is efficient, as we said, a very big positive, efficient. And what else? Benefits. Partitional algorithm would be really a benefit because category of algorithms. Uh, I think that's pretty much main of its positives. Some of its negatives are, we will come back because if I remember something else, I will add there. So negatives is, of course, k needed as input. So this is actually a negative in the sense that usually we don't know what is the intrinsic value of k for a given data set upfront. Because let's say if you have data set for students at lunch and you want to cluster them, so we don't really know how many clusters actually exists among that group. So, so if you want to be exhausted, then you'll have to try out many Ks. So which is of course a negative. Uh, okay? So K is needed as an input. Uh, so what else? From an optimization perspective, although I would say it's a slight negative, having it being an optimization problem is much stronger positive. But since this is non-convex optimization, so you are only guaranteed a local optimum. Okay? So you can say that from a purely mathematical perspective, this is a negative. Okay? So what else? It is sensitive to outliers. And why is that? And this is primarily because of the squaring of the error function. And error function is based on distance, Euclidean distance. So if an object is far away, its impact on the SSE, the cost would be quite high, and it might distort the cluster. It will move the center towards the outlier. So outliers would tend to impact the clustering quite significantly. So usually before applying k-means, sometimes we would like to remove outliers before applying k-means. So that is kind of a pre-processing that is somewhat recommended before applying k-means. Okay. uh, so that is one thing. The another thing with respect to the clusterings that it finds mostly having spelling mistakes, mostly spherical and homogeneous clusters. So why spherical? Because of course of the distance error function. Every object is determined, its error is determined as a distance from a central point. So the clusters it forms are usually spherical. Even if the data set does not have spherical cluster, it will find spherical clusters. And I can show you an example shortly on a slide. Just give me a second. So this is an advantage and disadvantage. Secondly, it does usually find clusters that are more or less of the same size, homogeneous size. तो लेट्स से आपके डेटा सेट में एक वो बहुत छोटा क्लस्टर है, एक बहुत बड़ा क्लस्टर है, वो उस तरह शायद नहीं ढूंढ पाएगा, वो ब्रेक कर देगा बड़े क्लस्टर को. ठीक है. So if the clustering is homogeneous, meaning that the clusters of the same size or the same density, then k-means would be able to find it. But if the densities are of different, of wide variety and of course the clusters of different sizes, then you won't be able to retrieve those clusters through k-means. And finally, there might be others as well, sensitive to initial clusters. So remember, when we started k-means algorithm, we had to select some initial means or initial clusters. So the algorithm in general is sensitive to that. So if you want to find better clustering, you'll have to start with multiple initial clusterings. Okay. And I think another point, let me add that. So it may give empty clusters, meaning that there might be some means may not get any object assigned to them. So let's say कोई आपके पास m था 3, कोई मीन था एक आइट्रेशन में, उस मीन को उस आइट्रेशन में कोई ऑब्जेक्ट असाइन ही नहीं हुआ, मीनिंग दैट के कोई ऑब्जेक्ट दैट all objects were closer to other object, not this object, closest to other object, not this mean. So it means that this cluster is now dropped. So oftentimes शुरू में आप जब k let's say 10 से start करते हैं, at the end of the day you might end up with only 8 clusters. You won't get k clusters. So this is a slight problem in the k-means algorithm. Okay. So now let's discuss some ways of overcoming these issues in practice. So we still have about 10 minutes, so I think we can do that. Any questions so far? All right. So of course for outliers, so usually remove outliers before k-means. Okay. And of course we have various techniques for removing outliers. We studied very briefly some in pre-processing, but we'll discuss more after this chapter. Okay. What else? So local minima issue. So run multiple times. So you can run multiple times with different Of course, this is time consuming, but if you want to find a clustering that is more global or closer to the global optimum, you will have to run the algorithm multiple times with multiple initial means. Okay. So what else? Uh, so then there's the issue of initial means. So for this, actually, there are a number of techniques that are available. So, so usually we'll choose k means randomly, but randomly may not give us good results. So what else can we do? So one technique that is proposed and it's common is to use points, objects, actual objects, not means, that are far away from each other at the start. So, so for example, you select one object randomly. So this is the first mean. And then for, let's say, I is equal to 2 to k. K is total number of clusters that you want. One cluster you have already found. Then you find the object that is furthest from the current set of means. ठीक है? Do you understand this? पहला आपने एक object ढूंढा. अब the next object would be the one that is furthest from this object. ठीक है? So second object, let's say ये ढूंढ लिया आपने. अब दो objects हो गए आपके पास. आपने तीसरा object वो ढूंढना है जो इन दोनों से सबसे दूर है. Of course you can do it as a sum. ठीक है? तो वो let's say ये object है, ये इससे और इससे दोनों as a sum सबसे दूर है. तो वो तीसरा हो गया. अब चौथा ढूंढना है तो चौथा ऐसा होगा जो इन तीनों से सबसे दूर है, मे बी इधर आ जाएगा, एंड सो ऑन. सो ये जो आपके पास पॉइंट्स आएंगे ये काइंड ऑफ डाइवर्स होंगे, एंड because of this diversity you may get a better clustering. So this technique, I think with this initialization, is k means को कहते हैं k means plus plus. Plus plus में खैर एक दो और extensions भी हैं, but the main extension is this idea of selecting initial points. ठीक है? Of course computational complexity थोड़ी सी बढ़ जाएगी, but that is only for the start. Okay. There are some other techniques here as well, but I think this is okay. I won't discuss those. Now, what about k as input? Remember, we said that k as an input might be a disadvantage. We don't really know the intrinsic number of clusters in a given data set. ठीक है? So इसमें of course भी कई techniques हैं. So one technique of course is brute force, is you run with different k's, and okay, वही है उसका. मैं फिर go to the slides. Okay, so what you can do is maybe you can plot on the x-axis is k, number of clusters, and the y-axis of course is cost. Yeah, SSE. Okay. So if you plot this, as you increase the number of clusters, you do clustering with different k's. As you increase the number of clusters, your SSE, your cost will always decrease, strictly decrease. Why? Because if you assume you have k is equal to n, then every object would be its own cluster and cost would be 0, right? So this curve would be strictly be decreasing. But it may have some kinks. So let's say a kink hota hai jahan slope significantly change ho rahi hai. So that those kinks would be a good indicator of the natural number of clusters in the data set. So if you run the algorithm for multiple k's and plot this curve of C, you might find from a visual perspective some kinks. Kinks का मतलब ये होता है कहाँ जहाँ slope significant change हो रही है एक जगह पे. तो वो k would be a potential k that you can assume to be a natural number of k, because उससे ये पता चल रहा है उसके बाद cost का impact एक significant change हुआ है. Of course, this cost slope would always be decreasing and it will eventually go to 0 when k is equal to n. But हमने सिर्फ वो points देखने हैं जहाँ वो एकदम थोड़ा सा slope में change आती है. तो वो potential points होंगे for our best number of clusters. So this is one way of determining and the number of k. Of course, again for this you have to run it multiple times. ठीक है, so ये हो गया and then of course empty. So empty clusters का issue of course can be reduced if you select initial clusters that are quite diverse. जो ऊपर हमने बात की थी selecting of initial clusters, उससे भी reduce हो सकता है. ठीक है, so so you can use that to reduce the issue of empty clusters. So another issue, another way that you can do this is maybe you can, whenever you're doing clustering, assigning objects to clusters, if an object that has the so furthest away from its mean, so in a way you can create its own cluster. On the fly आप एक नया cluster add कर दें, so that जो cluster पहले drop हुआ हुआ है वो इस वजह से add हो जाए. Make it its new mean, so that वहाँ एक cluster बनने शुरू हो जाए. So in this way, these are some tricks that you can use while you're running the k-means algorithm, so that you get good clusterings. And k-means algorithm, just like I would say a priori algorithm, the k-means algorithm, as well as let's say your basic probabilistic machine learning, these techniques are studied extensively. They have a lot of theory behind it, lot of practice, insights. So papers have been written on k-means since the 1960s, and they are still being published. So there's a lot of information available on the k-means from both theoretical perspective as well as from practical perspective. So you'll find lots of things. So I would strongly recommend that, at least for clustering also, I think I mentioned this last time as well, you should read the Introduction to Data Mining book, chapter 7. Not just the data mining concepts and technique, chapter 8, but also chapter 7 of Introduction to Data Mining. So that chapter is much more diverse and comprehensive. So मेरे ख्याल से we're running out of time. I'll probably stop here because there are a number of things, small things that needs to be discussed. So I think I'll pick it up from there next time. Any questions? Any questions? So we have a quiz in about 4 or 5 minutes. So no questions.